Schwab Hall style. Woot, woot. Um, we're going to be looking at shear stress distributions, otherwise known as I've been lying to you for most of the semester. So the same way that, like when we talked about normal stresses, how it's not uniformly distributed, it just you can say that it is for some situations, like if you have a long beam and you're looking right at the center and you're not looking near loads, it ends up being normally distributed. Or if you're talking about bending stress, because you have an unequal shear distribution, you're going to have an unequal stress distribution, or for torsional stress, it ends up being the same thing. Shear stress in general ends up being non-uniformly distributed. So let's have a look at something that looks like this. If I had regular old beam here, and say I have it in 3-point bending, just some simple load case, all right? So say P1, P2, P load, and you know that P1 equals P2 and P load equals twice any one of the supports, right? And that's just like our statics talking. Now, now what we have done with this is we've said, okay, we have this. I can draw a section through whatever part of this I want. I can draw this as a section. There's some of those a little bit. There's P1, and I have some shear force and bending moment, right? We've done that. In order to analyze the distribution of the shearing force and thereby the distribution of the shearing stress, we're going to back up to this full model and consider a stress cube inside of that. So if I just draw my arbitrary stress cube in there, I can pop this guy out, make it a little bit bigger, right? And there's some distribution of normal forces on it, right? Because the things in bending, so it has some normal force distribution on each side. There's also some shear stress distribution. And you throw the shearing stresses at it, usually like this. You have some like tau xy, tau yx, that's other tau xy, tau yx. Right? It's kind of familiar. Cool. All right. So we got something like that, and it's these forces that are going to be of interest. So let's try to sketch this out a little bit more. So this up here. I'm just going to redraw that beam quick. So I'm going to kind of draw the edge of my section there. Here's my little stress element. I'm going to draw it right up near the top. And now let's throw some dots in and say, hey, look, we got a load here. Here's a P1, whatever. You don't have to. It's kind of an arbitrary locations. The fact that I'm drawing in P load and whatever is kind of arbitrary. If I wanted to draw in stuff from bending, Might look something like that, right? Linearly distributed, and equal and opposite on each side, right? Okay. Now the $1 million per part of this is that you look back at our stress cube here. We got vertical forces, right? We also got horizontal forces. And we know that sum of forces and sum of moments on this stress cube are 0, right? So in order for so if I say that these horizontal guys, we know that those are equal and opposite at a point, right? Because it's bending. So those are all going to equal out. So in order for moments to equal out on this cube, all 4 of these shear forces that lead to all the shear forces that lead to these 4 shear stresses also have to be equal and opposite. So I'm going to ignore the vertical ones, and as long as I find one of these, I find all of them. So I'm going to ignore the vertical ones. I'm only going to care about a horizontal one. So if I go back over to this guy, because I've conveniently chosen an element that's on the edge of the thing, there's no force acting on this top edge, right? So I kind of cheat and found that one out. And we're going to say that there's some horizontal force acting on the bottom of this. It should be a shear force, right? Because it's acting parallel to the edge. We're going to call that delta H. All right. So if I did a summation of forces on this block, it's called stress on this side sigma A, stress on this side sigma B, so our normal stresses. If I did a summation of forces here, I get something that looks kind of like this. So got my delta H going to the right plus I did like an integral sigma A dA, because that's like stress times area gets me force, right? Be that minus integral sigma B dA equals 0. Where dA is just the differential area that comprises the side of this stress cube. Cool. All right. So because it's in bending, I know that I can find stress at any point along a cross section for something that's in bending, right? Just sigma equals my over I. We've done that about a bajillion times since now. So I can take it, and I can substitute that in, and let's say it's caused by some moment D and some moment C. Say like MA corresponds to MD. Sigma A corresponds to a moment D or whatever. All right. So if I substitute in this expression with a different moment for sigma A and sigma B, because they're going to be slightly different because they're separated by a little bit of space, right? Okay, and winds up giving me an expression for delta H, which is like my shear force. Looks something like this. And again, this is like a crazy derivation. Why would you ever need to know this? But it's good to know at least where some things come from. So you end up getting something like that, because the m y over i's get substituted into the integral sigma dA. M and I are constants. Y is not, because y is where you are along the cross section, right? So you end up getting left with the sigma y dA. So like, what does a sigma y dA remind you of?
The integral?
Yeah. Integral, integral y dA. Where have you seen something like that before? We've seen like something like integral y squared dA before, right?
Yeah.
What's that?
What the bending is it?
We actually did use it in bending. Yeah, if you think of like MYO over I, when we were deriving that, the I was actually an integral y squared dA. So y squared dA is the second moment of area, y dA is the first moment of area. We can also say it's like Ix, if you will. And because we like giving things names, we're going to call it Q. All right, so we got our delta H equals MD minus MC over I integral y dA. We know that we can call this like our first moment of area. But what about this MD minus MC crap? Because we don't know what either of those are. So we can take that and say, well, MD minus MC, we know that, so that's like some delta moment that happens across the width of the shear, of the stress element. We know that this stress element, this is really just a little tiny block that has a differential length dx, right? So if I pop back over here, I could say, well, I know how moment changes with respect to x, just dm dx times dx is dm, right? And so that's the same thing. So I'm going to abbreviate that, say it's capital V dx, where V is kind of the rate of change of moment with respect to x, which we also know to be what? If I take the derivative of my bending moment with respect to x, I get what? What relation have we noticed between our shear and our bending moment diagrams?
Slope?
Yeah, this is called the shear diagram. If I draw it for, I'm going to draw it for 3-point bending. Would be something like that, right?
Yeah.
And then bending moment for 3-point bending, something like that. So the derivative of bending moment is shear force.
Yes.
So dm dx is shear force, or dm dx times dx is really shear force times that differential length, the differential length of that stress cube.
Okay.
So we can say that that difference in moment is v dx. So if I go back to the equation for delta H equals v delta x over I integral y dA. All right, cool. We are moving and shaking. And I've said that y dA is q because we like having letters for these things. So v delta x, vq delta x over I is my shear force. But forces aren't stresses, right? So we need to translate that into a stress. So we do know that stress fundamentally is some force distributed over an area, even if it's a differential area. So in this case it would be like delta H distributed over the differential area of the bottom of the stress cube. So I could write dA, but that would not be helpful at all. But we've said that the length of this stress cube is delta x. We're also going to say that if I move this, if I extend this into 3D, the width of this beam is t, say. It's a thickness t. So length of the stress cube times t, that's like the area of the bottom face of my stress cube, right? So if I write this out again, so delta H over delta XT, which is like a tau XY now, that's a shear stress. It's a force, shear force over the corresponding area. So V delta X over I times 1 over delta XT, oh, and there's a Q in there, equals VQ over IT. That's my shear stress equation. Now it looks all nice and constant because like I doesn't change. That's related to the whole cross section. V doesn't really change because we can get that from our shear diagram here. At any point x, shear is a value that I can find. T doesn't change for any given point x either. Q is kind of our unknown here. It's that first moment of area, and what the crap does that mean? So in order to answer that question, we have to look at it at a particular section. So say that grab this guy, make sure that we use some values that are somewhat close, right? So if I look down like the edge of that beam, so there's my beam, it's got some forces poking at it. I'm going to grab a section and look at that section from like a side view, right? And say I got my stress cube up here, and it's a rectangle, so I know that the centroid of the stress cube is dead in the center of that. Okay. And when the centroid of the whole rectangle is here, say. Centroidal. Axis of section. This is centroid of stress cube. So let's call that Y bar, if you will. Y. Entire height of the whole section is H. And because it's a rectangle, it's half H above and half H below the centroidal axis for the section. And we'll call that C. Half H is C. With this puppy, we called it T before. Let's stick with that. All right? Mm-hmm. Cool. So, if I'm trying to find Q, just zoom out a little bit, give myself some room. There we go. So I'm trying to find Q. Q is the definition of the first moment of area is area times how far that area is away from a reference, right? Mm-hmm. So in this case, the centroidal axis of the section is our reference, so it's the area of that cube times y bar. This y bar is the distance from the centroidal axis to the centroid of the area. So the centroidal axis is the section to the centroid of that area. So if I wrote this out, I could say that A is the same thing as T times whatever this height here is. So that'd be like C minus Y, right?
Yeah.
Okay. Then Y bar to make sure this is, excuse me. That's interesting. If you go through enough of gymnastics, it'll work out. But y bar ends up being something like 1/2 C plus Y. Because Y is ultimately like the variable that we're kind of interested in including here, because it's, I'm going to say it, kind of like when we did bending stress, we were interested in how stress changes along the section. So it's probably the same across the section because our derivation didn't indicate any changes in with thickness, just with height. So we're only because that's how the bending stress was changing too. So we're only interested in changes along the y direction, the same direction the bending stress is changing. So we can drive all this thing into y, that'll help us. So we got this, and if we work out the math for it, it ends up being like t over 2 c squared minus y squared. We substitute this back into our original equation, which is like a tau xy equals dq over it, something like v over it times t over 2 c squared minus y squared. So as a result, what form does the shear stress distribution have? Is it linear, uniform, what? If we look at our section, remember in this case, like this is the y direction, and y equals 0 is like the center line, because that's how we treated it for bending, right?
Yeah.
Y equals 0 is was the neutral axis or the centroidal axis. So we're doing the same thing here. At y, let's see if we can plot this out. At y equals c, or if I look at here, this would be like at the top, the value of q goes to 0.
Yes.
So the shear stress goes to 0. So if I did like an axis here that was like magnitude of shear stress, I'd start at 0 up at the top. If y was negative c, I'd also get 0. So we know it goes back to 0. We know it varies according to y squared. So this is a quadratic distribution of stress. Shear stress is actually quadratically distributed. And we know that it reaches maximum when y equals 0, because any value of y is going to make this q smaller. So at the neutral axis, it's going to reach maximum. It's going to end up being distributed quadratically up to that and after that. So that's a pretty wonky little thing. So actually, whenever we look at like a bending stress problem, and we look where bending stress is at a maximum, which is at the top and bottom of a section, right? at those points, shear stress is actually 0, which is kind of weird. Meanwhile, if you go to the middle of the section where bending stress is 0, shear stress is actually at a maximum. However, if we work it out, kind of like how we saw that, like if I just pull on something versus bend something, bending gives me much more normal stress, like on like an order of magnitude. It's going to be the same thing with shear stress too. Shear stress will not give you as much stress as bending will, but because of Moore's circle, we have to account for how it's distributed in order to get an adequate estimation as to what the stresses on whatever your member are. So let's try a thought experiment here. So say that I had an I-beam. It's a really wide flange I-beam. So we came up with this quadratic distribution for a rectangle, right? And that's not going to change. I mean, this which we call this t over 2 c squared minus y squared thing is going to hold true for any part of this I-beam, right? But this expression isn't going to have the same numbers plugged into it. Like the thickness doesn't stay the same throughout this entire I-beam. If I drew like a stress cube here versus a stress cube that included like all that, right?
Mm-hmm.
Those two things would end up having multiple thicknesses. Centroidal whole location would change and all that thing, right? And as you might imagine, like the thickness here is much smaller than this by like 3 or 4 times, right?
Yeah.
So if I looked at shear stress distribution for an I-beam, say there's my upper flange, that's my lower flange, so like that's there, this guy is there, and this middle bit is that guy there, right? It ends up being something like this, where you start going quadratic, and then your t goes down by a lot. So the t that's back up in this equation, both here and here, how would you call it? Although you'd have to reformulate this q term, it goes way down. So shear stress actually spikes in the middle section, and then goes back down to almost nothing in the outer section. Excuse me. And if we wanted to, we could write out the equations for that, and which is calling he could get a value for that for Q that corresponds to the centroid of this cross section of this of this color, a different color of this orange section, so that we can, because we'll call it Q equals A y bar, right? So as we expand this section down through here, we have to account for the area of this entire orange section. We have to find the centroid of that entire section and all of that. We might actually have to do it in like 2 or 3 parts, right? Or really, it's going to be a symmetric distribution because the part's symmetric. So as long as we find Q up until this centroidal axis, we can just mirror it on the other side. But we're going to have to solve for at least 2 different kind of cases here. The case where we just have this top rectangle and it's relatively straightforward, and we have the top rectangle and some of this middle section, the shear web, as it's called. I-beams are made out of 2 parts. One is this top bit, which is a flange, and this middle bit is called a shear web, because its sole purpose is to absorb shear stress, because bending stresses are almost zero there, or they're almost entirely taken up by the flange. It's the shear stresses that get very, very large in that center bit, and you have to design that section to take care of that, which has actually been a big thing with composite materials. So if you think of it from like a more circle kind of view, we can predict what direction those stresses are going to be in. So if we just add a lot of strength in those directions, we're set. And the neat thing with composite materials is that you can do that very directly. So that's fun. Last thing about this, we got an eye here. What second moment of inertia should we compute for that? What way is this section rotating in a sense that we should compute I for? Should be this way or this way? Or in a real weird sense, think this way. Hey.
It wouldn't be that word one.
No, it wouldn't.
Why not?
So
That's how we rotate the beams.
not quite. So we got that weird eye from, we got the eye in there from bending, right?
Yes.
So this guy in three.
So it would be an X.
Yeah. So it'd be the same eye that would correspond to computing the stress from that bending moment. So in this case, if this is the x-axis, say, then the I would be an IXX. The second moment of area for something that was bending around that horizontal x-axis. All right?
Yep.
Cool. So those are shear stress distributions in a nutshell. I might throw you a couple problems to do on this, but primary homework for this month is the final project. So it will be a light assignment.
So the final project is homework?
The final project is your homework for this month, primarily.
Okay.
Yeah, I might give you a couple of light problems that
Okay.
deal with this, or one other thing that I have to do this week. But yeah, that's all I got for you.
All right.
Thanks for stopping by.
So then